Today we're going to think more about sequential events. And so a sequential event is something that is considered a multi-stage experiment. So a very simple example of a multi-stage experiment is that you flip a coin. That would be stage 1. And in the next stage, then you would roll a die. So that would be stage 2. So right now we'll get into a new idea, something called conditional probability. And in a nutshell, conditional probability is trying to determine the event or determine the probability of a second event occurring, given that a first one has occurred. Given that a first event has occurred. And so we will use a notation that kind of works like this. P, and unfortunately I'm using the one that the book has talked about here. So event B would be considered the first event, and then whatever you put in this slot is considered the second event. And the point of the story is that the probability of the second event could change based on what happens in the first event. So for example, if event 1 is drawing an ace from a deck and you have no replacement, or I should say drawing a card from a deck and no replacement, and then I say, okay, event 2, let's draw an ace. So what would the probability of an ace be? Well, it would very much depend on what happened in the first card. Did I draw an ace from the first card? If I did, then there would only be 51 cards left, and there would only be 3 left for me to draw on the second time. If I didn't draw an ace on the first card, I would only have 51 cards, but 4 aces available. So you can hopefully see that the outcome will change depending on what happens first. Okay? So basic formula. I'm going to try to illustrate things with a Venn diagram. Here's set or event A and event B. Okay? So assume event B has occurred. So this would be stage 1. Okay. What happens is that you can think of the sample space initially before any of the stages happens. Anything in the sample space S could happen. But then in stage 1, you assume that event B has occurred. So that means you're going to reduce your sample space essentially down to whatever has happened in B. That means in stage 2, you are going to ask a question like this. What is the probability of A occurring given that B has occurred? And so now what we've done is reduced our universe, reduced our sample space to all of box B. There is some portion of it that also has A's. So remember, this would be A and B. So if you are interested in the chance that A is going to occur given that B has, we use this definition. We'll write this notation. This is called conditional probability. This says, what's the probability of A happening, assuming that B has happened first? We are going to compare the area of the part with A to the area of the whole thing B. And because areas are synonymous with probabilities, then we make this definition. That is going to be the size of the part that has A compared to the entire part or the area of B. So I'm just interested in the ratio of how much of A fills up B. And so this is what's called conditional probability. If you know that B has happened first, you restrict your world to the box B, and within that restricted box, you say, how much of it is taken up by A? What's the chance of me hitting an A within that box B? So you can rewrite this as a multiplication rule for an intersection. So we can also reorganize this and say the probability of these two stages happening, B and then A, is a multi-stage product. First, it says you need to know the chances of getting B. That would be stage 1. Then you would multiply it by the chance of getting A, given that you know B has occurred. So that would be stage 2. This first example has to do with car repair. Okay? So a car repair can be either on time or late, and then could be either satisfactory or unsatisfactory. So we are going to think of this as a multi-stage experiment. And the best way for us to visualize what's happening and understand the sample space is with something called a tree diagram. So the first thing that can happen is your car repair could either be on time, so we'll put T for on time, or it could be late, L for late. Given that it's on time, the job may be done well, so satisfactorily, or it may be done unsatisfactorily. Even if it's late, the job may be done well, satisfactorily, or it may be done poorly, unsatisfactorily. So if you were to follow each branch of this tree, my mistake, going from the beginning dot to each outcome dot gives you all the possibilities that could happen. Your repair could be done on time, and it could be satisfactory. It could be done on time and unsatisfactorily. It could be done late but done well, or it could be done late and poorly. So these are the 4 outcomes. They are telling us that there's a probability of 0.077 that a job is done on time. So following this top branch of the tree tells me that there's a 0.77 probability of getting a job done on time. And then they say if the repair, so given that the repair is on time, there's a chance, a 0.85 chance that it is done well or satisfactorily. What's the probability that a job is done satisfactorily and on time? So according to the definition, the multiplication rule, this requires us to know, first of all, that the job is done on time, probability of on time, multiplied with the probability of satisfactory given on time. So it's a 2-stage experiment. It has to be done on time first, then it has to be done well, given that it's on time. The multiplication rule just gives us a quick way to get these results. The probability of being done on time is 0.77. The probability of being satisfactory, assuming that it is on time, is 0.85. And so because this is a 2-stage experiment, the probability of being on time and satisfactory is just the product of these two, 0.6545. And in this sense, the multiplication rule is just a different way of stating conditional probability.